Okay, so we are going to continue our discussion of module theory. Today we will be talking about products and co-products in the category of R modules. So first, let us recall the definitions or the categorical definitions of products and co-products. So first definition is going to be the categorical definition of product. So we say that given two objects, A and B, of a category C, we say that P is the product of A and B if there exists morphisms. So we denote them pi sub A that maps P onto A and pi sub B that maps P onto B, such that for all objects Z and all morphisms phi sub A that maps Z onto A and phi sub B that maps Z onto B, there exists a unique morphism Z into our object P, which we're calling the product, such that the following diagram commutes. So this is the standard definition, the standard categorical definition that you'll see um, with a lot of categorical definitions in making use of the morphisms and how objects sit within the category. Um, Examples of this, of course, will be if we have two sets. Let's say we have sets A and B. Then we define their product. The standard way of defining it, we define A cross B, so their Cartesian product, to be equal to the set of all pairs, such that A is in A, B is in B. Right, so one can check that in the category of sets, the Cartesian product of sets, that satisfies the this definition of products. And what this definition really captures is it captures the way that the product sits in its ambient category, the way that it behaves uh, with respect to other morphisms. That's why these morphisms are so important, because it shows how the product behaves with regards to other morphisms and other mappings into the sets A and B. Um, so it really carries some more data than just saying that the Cartesian product um, is this set of ordered pairs. Um, so you have the Cartesian product with groups, you have the direct product of groups. We have groups G and H, and the direct product, which we also define G cross H, is going to be the same as the it's going to be the same as the Cartesian product with some extra structure, and that extra structure um, is carried through how we'll just say that this is equal to same as sets, and it carries with extra structure, and the extra structure, like I said, is that um, we can add elements of our product now, and we do that component wise. And so this satisfies this construction also satisfies the definition of product, um, the categorical definition of product in the category of groups. Um, so there's a lot of interesting constructions. We have this for our modules, which is what we'll be talking about today. This kind of construction where it takes the same group definition and then it adds more structure onto it by defining the action of the ring R on the ordered pairs. So this is the definition of the product. And now we will talk about the definition of coproduct. Right. So the coproduct is a little bit different um, than the product. Maybe less intuitive, um, but we'll give it a go. So we say that given two objects, A and B, of a category C, we say that an object C is the coproduct of A and B if there exists morphisms. So now we are going to denote these morphisms: iota of A, iota sub A that maps A onto C, and iota sub B that maps B onto C, such that for all objects Z and all morphisms phi sub A that map A into Z and phi sub B that map B into Z, there exists a unique morphism sigma that maps C into Z, such that the following diagram commutes. So it's the coproduct. So we always think of when we label things with the prefix co, that it kind of reverses the arrows. And we could see that these diagrams are very similar with all the arrows in the reverse direction. Um, so now, like we said, in sets, right, in the category of sets, uh, so the disjoint union, that's a that satisfies the categorical coproduct. Um, and again, with this definition, this not only tells you, doesn't just tell you the element-wise construction. It carries the data of how this coproduct sits within its ambient category and the way that it interacts with other morphisms and other objects of the category. So it's a very powerful definition, and it generalizes a lot of things. In groups, you have it's called the free product. Um, I'll write that down. Um, Now, so in groups, um, the product has a simple explanation, a simple definition, and the product, the Cartesian product, enriched with this element component-wise addition, um, this has a this satisfies the categorical definition of of products, but for coproducts in the category of the general category of groups, this isn't the case. There isn't like a simple, there isn't a simple definition that you have to go into the free products, and for this you need to know free groups, and it's a little more complicated than just defining, adding structure to the Cartesian product. Um, and this is kind of where the these categories kind of differentiate themselves. Some categories behave nicer than others. One category that behaves very nicely is a category of abelian groups. So it turns out that in the category of abelian groups, the Cartesian product, right? So G cross H, um, where G and H are abelian, right? The Cartesian product, this actually satisfies the definition of coproduct as well. So the Cartesian product satisfies the categorical definition of product for both groups and abelian groups, but the Cartesian product with this extra structure also satisfies the coproduct definition for abelian groups. So this is where the category of abelian groups and the category of groups, this is where they differ. They kind of differ in their coproduct structure. Um, and this is what led to the definition, or maybe not led to it, but this is one of the reasons why we enjoy abelian categories. They have very nice properties. And what we're talking about today is the category of R modules. And the category of R modules, we can think about it as kind of like an enriched category of abelian groups. And this certainly is an abelian category. So we have, just as a spoiler for what's ahead, the what we call direct sum. The direct sum of R modules satisfies both and the direct sum is just an enriched direct product of sets of the underlying sets. This satisfies both the categorical product and coproduct definitions. So let's get into that now. So now we're going to define the direct sum. So we let M and N be R modules, and we define their direct sum, which we denote with this circle with a plus in the middle. So this is the direct sum to be the set. So here we're just taking the Cartesian product. This is the regular Cartesian product. So we have pairs m and n, such that m is in capital M and n is in capital N. And we define binary operations on these sets, right? So we add element-wise or component-wise, and then we define an action of R, of the ring R, on our ordered pairs to just be the action of um, the element R on the individual, taking place in the individual R module structure. So this is a simple exercise. You can check that the direct sum, as we've defined it here, is an R module under the operation defined, the binary operation that we defined, and the action of R. So this indeed is an R module. But we don't know yet that it satisfies the categorical definitions of product and coproduct. So we'll go into that now. But first we note that the direct sum, so this direct sum comes with several homomorphisms, so several R module homomorphisms. So we have here, these are the, we have the projections. We have these projections and we have these injections. These are kind of like canonical. This is the canonical projection. So the projection onto the first factor, the projection onto the second factor, and then we have the injections into the first factor, injection into the second factor. We see that we just take take the other element to be 0, so that m sits inside of the direct sum as a submodule. Okay, so that's just an important note that with these, M and N are submodules of the direct sum. So this allows us to we can already kind of see how these are going to be playing into our definitions, right? So these will be used for in the categorical product, and these will be used in the categorical coproduct. Now, with these morphisms, we will show that the direct sum satisfies both the categorical product and coproduct definitions in the category of R modules. So we have our proposition. The direct sum satisfies both universal properties for the product and coproducts in R module, in the category of R mod. So we'll get right into it. So we're going to let P be an R module, and we're going to define two morphisms. These are R module homomorphisms. So we have phi sub m and phi sub m that map P into N and P into M. So these are two R module homomorphisms, and we know that in order for the direct sum to satisfy the universal property, there must exist a unique R module homomorphism, sigma. So our sigma right here, that maps this P into our direct sum, such that the following diagram commutes, right? So we're just given, so this is any R module, and these are any morphisms into M and N. We have to show that we can construct this sigma, and the construction of the sigma really is quite intuitive. Let's just see what we need to know. We need the diagram to commute. So we need first we need pi sub n composed with sigma. We need that to be equal to phi sub n. But at the same time, simultaneously, we also need pi sub m composed with sigma to be equal to phi sub m. So and there's really only one way that we can define a morphism to make this diagram commute both on the left and the right at the same time. So the diagram forces us to define our sigma to just be, so sigma of p, we just take our morphisms in the components. So yeah, we define our sigma to be our original morphisms in the components. And this does make the diagram commute. That we could show that it does, right? So one of our um, one of our we'll show both of them. So we want pi sub n composed with sigma. So the first thing we want is pi sub n composed with sigma. We want that to be equal to phi sub n. So we see that if we have p and p, pi sub n composed with sigma of p, that's equal to, so we have pi sub n composed with sigma of p, and from our definition, we have now pi sub n of phi sub m of p, phi sub n of p. Now, pi sub n is the projection onto the second factor, right? So we project into n, and this will just be phi sub n of p. So, of course, we see that this definitely holds, and simultaneously, pi sub m composed with sigma applied to p, that's going to be pi sub m of the same deal as above, phi sub m of p, phi sub n of p. Now we project onto the first factor, we get phi sub m of p. So this does indeed satisfy the commutativity. So it simultaneously makes the left and the right side of the diagrams commute. It's an R module homomorphism. This is a simple check because each of the factors are both R module homomorphisms, and this definition satisfies it trivially. Uniqueness is also we really don't even need to check uniqueness here because we are forced by the diagram to define it this way. So this satisfies the definition of product in the category of R modules. So now let's show that this also satisfies the definition of coproduct in R mod. So we're going to show that the direct sum satisfies the universal property for coproducts. Now for this, we let P be an R module like before, but this time we have two R module homomorphisms. We have psi sub m that maps m into P, psi sub n that maps n into P. So these are two R module homomorphisms. So as we said, we're reversing all the arrows, and for the um, m direct sum n to be a coproduct, we must have a unique R module homomorphism sigma that maps m direct sum n into p such that the diagram commutes. So again, we could look at the commutativity conditions. So we know that we're given these. These are our canonical injections that we were defining before. So we need both at the same time. We need sigma composed with iota sub n that has to be equal to psi sub n, and we also have to have that sigma composed with iota sub m that has to be equal to psi sub m. So we need both of these conditions to be satisfied at the same time. Now the definition for sigma in this case is a little less intuitive, and it comes from the definition of sigma when we talk about the coproduct in the abelian category, in the category of abelian groups. Now, in this category, we could expect, since we are taking advantage of the, we're going to be taking advantage of the abelian nature of our underlying groups in the definition of sigma, which is why this will not work as a definition for coproduct in general groups. So in order for the in order for this morphism, um, in order for this to satisfy the definition of coproduct, we're going to define sigma that maps our direct sum onto P by, so sigma of m and n. So we're going to take a pair, an element of the direct sum, and we're going to map it to psi sub m of m plus psi sub n of n, okay? So we're going to take our two elements and we're going to add them based on their images under psi sub m and psi sub n. And we're going to show that this is the required homomorphism. So first we're going to show that it is indeed a homomorphism. So we're going to be given, we're going to do the standard check. So given two elements of our direct sum, we have sigma of m sub 1 n sub 1 plus m sub 2 n sub 2. We add these together in our direct sum, so nothing crazy yet. So that's going to be psi sub m of m sub 1 plus m sub 2 plus psi sub n of n sub 1 plus n sub 2. And since psi sub m and psi sub n are both R module homomorphisms, we can split these up. So we get a nice long summand. Now, from this step to this step, this is where we take advantage of commutativity. This is where we take advantage of commutativity, where we can swap the summands around. So we're going to bring our n sub 1 over here, and we're going to bring our m over here. We swap these two middle guys, and we have our desired homomorphic property. So this is indeed a group homomorphism, and we see that in the general category of groups, this would not work. So this only works in the category of abelian groups. Yep, so we see trivially, as I put it here, that the composition sigma composed with iota sub m is equal to psi sub m, and sigma composed with iota sub n is equal to psi sub n. Okay, so how do we see that? Well, if we have, we see that if we have a, so we could write this down over here. So maybe we'll make a little note on the side. So for this guy over here, we see that sigma composed with iota sub m, let's say applied to m, well, that's going to be equal to sigma of, now we know that iota injects m onto our element m comma 0, okay, and then we know that sigma, so sigma of m0, that's going to be equal to, right, that's going to be equal to psi sub m of m plus psi sub n of 0, and we know that psi sub n of 0, that must be equal to 0, so this is just going to be equal to psi sub m of m. And we see the same thing for sigma composed with iota sub n, so that's well and good. Now we're going to show that it's unique. Okay, so we're going to suppose that there's another morphism, sigma prime, that maps m direct sum in into P such that the diagram commutes. Okay, then for all m and m comma n in the direct sum, we have, so here we're going to split up the summand into m comma 0 plus 0 comma n by commutativity, right? Because we're assuming that there is another sigma prime that makes the diagram commute. So we have this picture here. So with this picture here, we're assuming that we have sigma prime that makes the diagram commute, so we can split this guy up. So this is going to be the same iota m, and this is the same iota n. This is psi m, this is psi n, right? So we can split this up into sigma prime composed with iota m, because we know that iota, well, first we know that here we can write this as sigma prime of m comma 0 plus 0 comma n, and because sigma prime is a morphism, an R module homomorphism, we have sigma prime of m comma 0 plus sigma prime of 0 comma n. Now, we know that m comma 0, that's just the image of m under iota sub m, right? So that's where we get sigma prime composed with iota sub m of m, because we know that iota sub m of m is equal to just m comma 0 plus sigma prime composed with iota n of n. So that's where we get that condition. But by commutativity, right? So this is the commutativity step. We know that this is equal to psi sub m of m, and this is equal to psi sub n of n. But we know that by definition, this is indeed just sigma of m comma n. So we've shown that this is a unique morphism, and it's in R module homomorphism. It inherits these properties from psi sub m and psi sub n. We could leave that as an exercise. It's a very simple check, but they do indeed satisfy the R module homomorphism properties. And so we have shown that the direct sum of m and n satisfies the coproduct universal property as well. So just to recap, we've shown that the direct sum of R modules satisfies the categorical definition of both products and coproducts in the category of R modules. This is one of the components to that make the category of R modules an abelian category, which is a nicer category to work in.